Hello and welcome to Numeristical. We are kicking off a new video series today on building gradient boosting models. So in this series, we're really going to go step by step and give a roadmap of how you should approach building models and specifically gradient boosting models from start to finish. So we're going to go through all the practical issues that come up, and we're going to sort of give this roadmap, and then we're going to go through and execute this roadmap. And this will involve things like how do you explore data, how do you build your first baseline model, how do you iterate and improve your model, how do you go about feature engineering, and how do you set the hyperparameters. So in this first video though, we're going to be more big picture and more motivational. So we're going to talk about how model building has changed over the years as we've gone from small data sets and primarily using things like linear regression to these bigger data sets and tools like gradient boosting. And we're going to talk about, for example, the train test paradigm and some of the issues that come up, how you choose your train and test sets appropriately to avoid things like leakage. So this will be an overview and really set the stage for some of the practical issues that you're going to run into when you use this approach on real data. So I hope you'll enjoy it. Before I get into the lecture, again, I'd like to ask you if you please like the video and subscribe to the channel because that really helps me out. And with that said, let's get into the lecture. Hello and welcome to the course on building gradient boosting models. In this course, we're really going to take a very detailed step-by-step and hands-on approach to how to build gradient boosting models in practice. We'll talk about how to deal with hyperparameters, how to iterate, and so forth. So let's get right into it. I'm going to put up the outline for this class. So to start out, we're going to do a little bit of motivation where we talk about classical versus modern data analysis. And we're going to sort of compare and contrast how things were done kind of in the old days when you had very small data sets and very relatively simple tools like linear regression, and compare it to the modern approach where we have much bigger data sets. And one of the big things we'll talk about is the train test paradigm, because that's one of the big things that having a data-rich environment has enabled us to do. So we'll talk about the contrast between those two methods of analysis, approaches to data analysis. Then we'll talk about model building principles, and we'll really go through and detail out a model building process for how you should go about approaching building models and models in general, and especially gradient boosting models. And I should add, we're going to get really hands-on starting in this section. We're going to start going into a notebook and dealing with real data and building a model to illustrate these steps in action. So we'll talk about dealing with all the hyperparameters in gradient boosting models. This is something we'll deal with along the way. And specifically, we're going to talk about how to use early stopping to deal with the issue with the number of estimators and the step size, that those two variables being very interactive and also interactive with the max depth. So we're going to talk about an approach that I recommend of how to deal with those three very, very important hyperparameters. And then we'll talk about how and when to go into full hyperparameter tuning. And in general, we'll talk about an approach for iterating and improving your model. So to start out, let's give just a little background, a little overview of classical data analysis versus what I'll call modern data analysis. So in classical data analysis, a long time ago, data sets used to be much smaller when people did data problems. A lot of these tools were developed with an eye towards much smaller data sets. So data sets would typically be less than 1,000 data points and often less than 100 data points. And there's also a lot less computing power. So linear regression was really kind of the tool of the day at that point. And what was so great about linear regression is that it had a closed form solution. And it generally underfit. There wasn't that much risk of overfitting. And since we had small data sets, there wasn't too much to be gained by trying to use some of the advanced methods we have now. Probably would not have added too much power because the data sets were so small. So in this small data paradigm, what are some things that you have to do when you don't have that much data? Well, for one thing is that the data that you use for fitting your model ends up being the same data that you use for evaluating your model. So if you've only got 75 data points, you don't usually have enough. You don't want to throw away 25 out of 75 data points to have a holdout set. So typically they would just fit the model on the data and then evaluate the model on the same data. And we'll see some of the implications of that. So some of the metrics that were commonly used at the time, and they're still used now, but a metric like R squared, for example, was a very commonly used one for a linear regression problem. And one issue with R squared is that it would only improve with model complexity. So if you do a linear regression with 3 predictors, you get a certain R squared. When you add a 4th predictor, your R squared can only go up. It can't go down. So this made it hard to evaluate whether you're really improving your model by adding that 4th predictor in this case. So the way this was approached at the time, since we didn't have a separate test set to look at, was they would use kind of surrogate metrics that would trade off the model complexity with the fit to training data. So as an example, there were things like the adjusted R squared. The adjusted R squared would kind of control for the number of variables and say, hey, if I added in a variable, but it didn't really improve my R squared that much, the adjusted R squared might actually go down, and that'll be some indication that although my R squared went up overall, I'm probably not getting as much bang for the buck out of this predictor as I should expect. Similarly, there were criterion like AIC and BIC, and these information criterion type metrics, the way they would work is they typically have one term that judged how well your model fit the data, and then another term for model complexity, and you would trade off those 2 terms. And in general, in this small data world, you would use techniques that had very low risk of overfitting. So models were typically underfit in that the real world was considerably more complex than what the models showed, but since you had a small data set and you had to stick with more simple techniques, you generally just get an underfit model that would, demonstrate a little bit about what was going on, but were not as complicated, as interactive, and as interesting as the models you can fit now. So these models generally underfit because they had such a low risk of overfitting. Now, one bit of wisdom that came out from this old way of doing things is that it was considered bad if your model performed worse on out-of-sample data. So you'd fit a linear regression on your model. Let's say you had 75 data points. You fit your model. You're happy with it. You did whatever art and science you had to get the best possible model. Now, later down the road, let's say, you get another swath of 50 data points, and you want to see, hey, how well did my model do on those 50 data points? And if the model did a lot worse, there would be a sense of like, we did something wrong. We must have overfit somehow on this data because we did so much worse. And I still hear that sentiment echoed that like, if you're doing worse on out-of-sample data than you did on your training data, then that's something bad, that's something to be concerned about. And as we'll see later, that's actually not true in the modern data paradigm. In the modern data paradigm, you typically, quote unquote, overfit to your training data, meaning the training data is not supposed to be representative of your performance on out-of-sample data. And it's okay if you do worse, and it's totally expected if you do worse on out-of-sample data. So let's talk now about what I'll call the modern data paradigm, or bigger data paradigm, or what's also called the train test paradigm. So in this way of acting, we're in a regime where data is plentiful. We really have much bigger data sets. We have a lot of data to work with. So we have a little bit more flexibility in how we approach these problems. And because of that, one of the first things you do if you say you have enough data is you say, I'm going to hold out some of the data for model evaluation. And so I'm going to have one set of data where I build my model, do all my tricks, do all my algorithms, try everything out. And then I'm going to use this other data set that's a whole bunch of new data points. I'm going to use that to judge how well the model is working. So you've got the training data, which you use for fitting the model. And then you've got test data, which is used for evaluating the model. So after you build your model on the training data, you then use that model to make the predictions on the test data. And you evaluate the quality of those predictions on the test data. And you can repeat this with different modeling choices, different algorithms, different features, different hyperparameters. And really the idea is you're trying to kind of set up a fair competition. And you can use techniques with high risk of overfitting because at the end of the day, you just care about what's the performance on the test set. So it's everyone's kind of, you could think about it as lots of competitors, different models, different settings, different approaches, different features. And at the end of the day, you go on the training set, you do whatever you want, you build whatever model you want, and then everyone gets evaluated on the test set. And if the test set is presumably big enough and representative enough of the real world conditions, then kind of whoever does the best on the test set is kind of the winner. Now you have to take that with a little bit of a grain of salt, but the idea is that we don't really care what the model performance looks like on the training data. In fact, we might not even look at how the model does in the training data because we expect it to be overfit, we expect it to be unrealistically good. And that's not really the point. The point is to see who does the best on the test set. And this train test paradigm has really been really important and influential because it's enabled people to try out more complicated methods, things that have higher risk of overfitting. And I think a lot of the advances in neural networks and so forth were done by breaking a lot of the conventional wisdom about how many parameters a model should have, for example. It used to be conventional wisdom that you should never have more parameters than you have data points. But this is routinely broken now with deep learning, and most neural networks have way, way, way more parameters than data points. And it was really the advent of this train test paradigm that let people sort of break the rules a little bit and demonstrate that even though I'm breaking this conventional wisdom, I'm doing better on the test set than the other methods. So at the end of the day, that's a better model. So let's talk about the test set. And I would say there's really two purposes of test set evaluation. And it's important to keep them both in mind as you work on your model. So the first, and I would say more common one that people think about the test set is to compare different models. And this gets at what I was just saying. You want to have a fair fight where you say, hey, everybody gets to train their model on this training data. You can do whatever you want on the training data. And then I'm going to give you this test data, and we're going to see who does the best on that. So you can compare different algorithms, different choices of features, different settings of hyperparameters, and so forth. And at the end of the day, you kind of use that test set to say whoever did best on this test set is doing the best. And you might have a little bit of adjustment to that, but more or less that's what you're saying. Now the second purpose of test set evaluation is to get an absolute sense of performance. So you might want to know, okay, when I take this to production, when I use this in the real world, how well is it going to perform? And that's why you have the test set, because the test set, the model didn't look at the test set during training. So it should give you a relatively good sense of how it would perform on new unseen cases. Now again, you have to be careful because often your test set may not actually be representative of the real world conditions that you want to use your model on. So you always have to consider that possibility as well and make adjustments for that. Now what I just described was kind of the most standard version of the train test split. But there are some extensions to this that can be used in more complicated situations. So sometimes there's a third data set that's used, and it's commonly called a validation data set, although that nomenclature I think is sometimes misleading. But this is data that we use during the model fitting process, but that does not directly affect the model. So what do I mean by that? Well, the most common example of this is in early stopping. So as we've discussed in previous occasions, when you're building a gradient boosting model and you're sequentially fitting these trees and trying to improve your performance, reduce the errors made by the previous collection of trees, it's hard to know what's the right number of trees to build and when you should stop. Because on your training set, typically your error will just keep getting lower and lower and lower. So a common approach is to have a separate set where you just evaluate the model at every iteration. And you say, when I'm starting to do worse on this validation set, at the beginning, typically, you're going to improve on your training set and improve on the validation set and improve on the test set if you're looking there. But then at a certain point, the performance will start getting worse on the validation set. And that's the sign that these additional trees that you're adding are really just fitting noise. They're not capturing any useful signal that generalizes to the validation set. So you could use the test set for this purpose, and it is commonly done, and it's not really that huge of a problem, but it will be a little bit misleading. If you use the test set, then when you go to evaluate your performance on the test set, you'll be a little bit favorable because you picked exactly the perfect point to stop for that test set. Now, if I'm comparing a bunch of models, that may not be a problem because I'm kind of cheating a little bit, but I'm using the same kind of cheat for all of my different models. They're all getting the best exact case on the test set. So that may not be that big a deal. But to be completely fair and completely sort of dotting all of your I's and crossing your T's, what you should really do is have a separate validation set that you use to find early stopping, and then again use the test set for its overall purpose of getting your evaluation metrics and getting a sense of how you might perform in the real world. So, as I just said, sometimes just use the test set as the validation set. Slight cheat, but it's usually okay in practice. Next, let's talk about cross-validation. So, cross-validation is an alternative to the standard train test paradigm, or you could think of it as an extension. And the way it works is as follows. We're going to divide the data into what we call folds. And you can just think of folds as being sort of buckets of data. So imagine you have your whole data set, and every data point you assign to one of, let's say, 5 buckets. And you try to keep these buckets about equal in size. They don't have to be exactly equal, but roughly equal in size. And now what we're going to do is we're going to kind of do our train test paradigm, but we're going to rotate what our training set and what our test set is. So for example, I could say first I'm going to use folds 1, 2, 3, and 4 as my training set, and fold 5 as my test set. So this would be like an 80-20 train test split. And I can do that. I can train my model in 1, 2, 3, and 4, make my predictions on 5. So now I've got some predictions on fold 5 that came from a model that didn't see fold 5, it only saw folds 1, 2, 3, and 4. So the predictions on set 5 are sort of a fair representative performance of how the model might behave on out-of-sample data. Next, we're going to rotate the roles of the training and test set. So last time the test set was fold 5, now we're going to make the test set fold 4, and we're going to train on folds 1, 2, 3, and 5. So I'm going to have a slightly different model because I've got slightly different training data. Now look, in this case, about 75% of the training data is going to be the same because folds 1, 2, and 3 were common to both training sets. But there'll be a little bit of data that's different because I'm training on 5 now, and what I predict on is going to be different. And I can repeat this process where each fold gets its turn to be the test set. So next I would have 1, 2, 4, and 5 be my training folds, and 3 would be my test fold. And then 2 would be my test fold, and then 1 would be my test fold. So I'd repeat this 5 times, and each fold would get its chance to be the test data. So at the end of this, I've got a set of predictions on the entire data set. And one of the reasons to use cross-validation is if you don't quite have enough data to do a single train test split. So for example, let's say you've got 500 data points. You could say I'm going to use 400 for training and 100 for test. But perhaps you're concerned that 100 data points really isn't going to be enough to reliably evaluate which model is better, right? So the bigger the test set you have, the more confidence you could have when you say, hey, model A did better than model B on the test set, so model A is going to do better overall. Because if you've got a really big test set, that's a lot of evidence that model A is doing better. If you've only got 100 data points, though, maybe you say that's not really enough. I mean, maybe model A is getting lucky on this test set. Maybe for this small sample, A is doing better, but maybe B is really better in the long run. So, if the advantage of using cross-validation is that you're going to effectively use the entire data set for both training and testing. But let's continue with our process. So after I've got these 5 predictions on these 5 different folds, I've now got a set of predictions. They come from 5 slightly different models, but all the models are somewhat similar because any 2 models are going to share 75% of their training data. So I've got 5 slightly different models, and I've got a set of predictions now across my whole data set. And we're effectively using all the data for training and for testing. So the predictions come from slightly different models. Now, once I choose the model, so let's say, imagine I do this cross-validation process now for a couple different models and a couple different hyperparameter settings. I repeat this whole process. And I decide this model with these settings, this is the best one. Now I can retrain my model on the entire data set, all 5 folds, and sort of put that out as my final candidate model. Now, one of the cons of cross-validation is that it's costly in time because I've got to do 5 iterations of model fitting for each variation rather than just one. And then typically, because we do this final refit on all the data, it's effectively 6. So if we do 5-fold variation, you actually have to do about 6 model fitting runs, which can be a lot more time consuming if it's a method that takes a long time to run. The other disadvantage is that we're going to be using slightly different data sets. The data sets of each of the models of each of those 5 folds are slightly different from each other, and they're going to be slightly different from that final model. So you're kind of taking a little bit of a leap of faith that the differences between the different fold-based models and your final model, that all those differences kind of don't make too much of a difference. If you have some hyperparameter settings that worked well on average for each of those 5 models, the 5 fold-based models, those settings will also work well on the final overall model. Next, I want to talk about something called leakage and how to prevent it. So you may have heard this term leakage. And it's hard to get a really good definition of leakage, but what I'm going to say is that leakage occurs when the training data contains information about the test set that unrealistically improves performance. So let me walk through an example of a case where this might come up very innocently. Now, you can have leakage happen like in really silly ways where you just sort of, when you took your train set and your test set, you actually used the same data set both times. And so then you're obviously going to get leakage in that case. But sometimes this can happen in a more subtle way. So let's talk about an example where that might happen. Let's say you have a data set that has transactions from a coffee shop. So you've got a big list of transactions, and your goal is to try to predict who orders food based on the demographics of the customers. So let's say somehow they're paying with credit card or something, and you're able to get, age and their job and their height and weight or whatever it is, a bunch of demographic information about the customer, and you're able to see, did they just buy coffee or did they also buy food? So maybe you're a cafe, you're really interested in, you realize you need to have people ordering food to make the economics work, so you're trying to predict, who are the people that order food. And now one of the challenges with this is in this big set of transactions, you're going to have repeat transactions from customers, right? So the same person might go to the coffee shop multiple times. And what will happen if you just took your big transaction set and you just randomized and you said, hey, I'm going to put 80% in train and 20% in test, and there are customers that came in 10, 20 times, you will have transactions from that customer in both the training set and the test set. Now, this might reward overfitting, right? Because if you imagine in this coffee shop, people tend to order the same thing. A lot of people just go in and they order the same thing every time, right? So your model, for example, let's say there's a 32-year-old, 210-pound lawyer, and this person always orders food. Now, in your training set, your model will have, let's say, 7 of those transactions of this 32-year-old, 210-pound lawyer, and it will say, oh, okay, if I can pump up the probability that they order food, this will always improve my training set performance. So with every iteration, it tries to boost that up a little bit, specifically for this particular combination of features. And what's going to happen is on the training set or the test set or the validation set that you're using, this will always get rewarded because you've got 3 transactions of that same person. So it'll say, yeah, you're doing great, keep doing that. And it won't, early stopping won't kick in or anything because it won't kick in for this particular example because you're always doing better on both the training set and the validation set. So this is a more subtle example of leakage. So the model learns this, and it helps on the test set or the validation set, whatever you're using for early stopping. But now, when I take this model and I use it, let's say the intention of my model was to use it to evaluate, a new market or something. It's going to say, oh wow, you've got a 32-pound, 210-year-old lawyer in this other market. Oh, that person will always order food, no problem. Like 99.9% that person's going to order food. And that's not what you want. So it's unrealistic in that it kind of knows the answer. You had transactions about this exact person, and it's fitting the behavior of that particular person, but it's not really capturing the general probability of ordering food of 32-year-old, 210-pound lawyers. So one solution, how would you deal with that in this case? One solution would be if you separate your train and test set by customers rather than just by transactions. So if you had like a customer ID where you could identify that all these transactions are from the same person, maybe a better way to create your train and test set or your cross-validation folds, if you're doing cross-validation, is to make sure all transactions from a particular customer end up in the same set. If it's cross-validation, make sure they end up in the same fold. If it's train test, make sure they're all in the train set or all in the test set. Another way to do it, if you're worried about this particular type of data can bring up lots of issues, so I'm only scratching the surface of it. Another thing you might do is limit your data to 1 transaction per customer, right? So that's another way that you can eliminate this issue. This is something that comes up a lot where you have transactions and customers, and different transactions of the customer might vary a little bit, but they don't vary as much as they will overall, and you have to be very careful about how you want to handle it. So just want to bring up another way to handle it would be to limit the data set. Of course, now you're reducing your data size, which may or may not be good depending on your application. So this discussion of leakage brings up some important ideas about how you should choose your data sets, your folds. So as we just saw, a lot of times it makes sense to stratify across what I'll call entities. So when you're choosing your train and test set, in the case we saw before, if you know that lots of your transactions come from the same customer, you might want to choose your train test set so that all the transactions from a particular customer either all end up in the training set or all end up in the test set. to avoid this leakage problem. And the way I might describe that in general is you might want to stratify across entities. So if multiple rows in your data set have some common entity, they're either for the same person or the same client, so forth, it's often a good practice to make sure those all end up in the same set. Either they're all in the training set or all in the test set, and this will help you avoid some of these leakage issues. Another way this comes up is when you've got time series based data. So for example, you might have, you're trying to predict something that varies across time. Now if you have transactions from that time, so you're trying to predict, you want to build a model, you're in 2023, and you've got data, let's say, that runs from 2000 to 2022, and if you just randomly scramble those transactions, you might do a good job of predicting what happened because you had some future signals. So for example, like COVID, right? Like if you're trying to predict sales across time and you had data from the COVID era in your training data, you'd do a lot better at predicting what your sales were in the COVID era. Whereas if you stratified in time, it would be a lot more realistic because you would only have, you wouldn't be able to look into the future and see that signal from the future. So again, you want to make sure that your training set and your test set cover different time periods when you're stratifying time, if you expect that that's going to be contain an important signal and you expect that your production environment, will not be able to capture that signal. So again, if you expect strong time-based variation, it might be important to stratify in time. If you expect strong entity-based similarity, you might want to stratify by entities. And sometimes you might have both, and you might have to do clever things to be able to stratify in both directions. Now this also applies to cross-validation, so just like you want to make sure everything ends up in the same trainer test, either in the train test or the training set or the test set, you similarly want to make sure all of these similar things end up in the same fold for cross-validation. And the general principle you want to think about here is that the relation between your training and your test sets should reflect the operation conditions you expect in production. So if you're going to try to predict things in the future and you know that things change over time, you want to make sure that you're, the best thing to do is have a training set that goes up to a certain date and then have a test set which goes after that date. And that will really mimic the conditions you'll have in production, because in production you're not going to be able to see into the future. Hope you enjoyed that. In the next lesson we're going to really go through the model building principles and really give the step-by-step of how you should go about building a model, and we'll start working with real data in the next video with Jupyter notebooks and so forth. So I hope you'll join me for that next one. Before you go, again, if you could like the video and subscribe to the channel, it would really help me out. And with that, have a great day.